The last thing we're going to talk about this week is mechanisms of heat flow. And there are three that we're going to discuss that are significant, and they all have their own particular types of materials that they're most significant in. The first mechanism is radiation. This is the transfer of energy through the emission and absorption of light waves. We're going to specifically think in terms of long wavelength light, so-called infrared, which is what we, humans, perceive as heat. This travels through space. It's the only mechanism that actually works when you have an absence of a media, so it works in a vacuum, whereas the other two mechanisms do not. So this is the sole mechanism in free space. It's important in gases, along with our next methodology. Generally does not occur very much in liquids, and its effect on solids varies a lot depending on the solid. Radiation is very significant when you're talking about glass. Radiation is not at all important when you're talking about a desk. Convection is the transfer of energy through the bulk movement of material. So the classic example of this is like a heater in a room that heats a block of air, and then the heated air moves throughout the room. Could be passive, could be active, could be driven by a fan, for example, which would make it active. But it depends largely on the transfer of heat from some source into the gas or liquid, and then the movement of that gas or liquid throughout its container. This, of course, does not occur in solids because the molecules in a solid are fixed in place. Lastly, we're going to talk about conduction, which is the transfer of energy directly from molecule to molecule. This is most important in solids. It is the primary means of heat flow in solids. It also occurs in liquids and gases, but it is generally so overwhelmed by convection that it is not important to consider conduction when talking about liquids or gases. So, to check that off, radiation, free spaces, and fluids, convection, fluids, and conduction, solids. The radiation rate of heat transfer depends on the area of the thing that's doing the emitting. So we're going to just assume this sort of little amorphous blob. Heated up to some temperature higher than its environment, and it's going to give off heat at a rate that depends on the area. A larger object is going to give you a greater rate of heat transfer than a smaller one. The emissivity, which is a property of the material, and it's related in part to color and finish and things of that nature. So a high emissivity object would be like a flat black frying pan, or the radiator in a car, or some dull surface that emits and absorbs heat very easily. A poor emitter would be, for example, a mirror, which would be reflective instead of absorptive or emittive. So a perfect mirror would have an emissivity of 0, and a perfect absorber would have a reflectivity of 0 or an emissivity of 1. So we're concerned with emissivity here, so we're looking for values between 0 and 1. A property of the universe that we call the Stefan-Boltzmann constant comes into play when talking about radiation, and it is the amount of heat that can be carried by a given photon, the amount of energy, if you prefer. And also the temperature of the emitting object, the temperature of the absorbing object. And what we're really going to concern ourselves with is the difference between the temperature of the object and the temperature of the surroundings. So a hot object surrounded by hot surroundings is going to absorb and emit roughly the same amount of energy if it's in the same temperature as its surroundings. A hot object surrounded by cold surroundings is going to emit much more energy than it's going to absorb. An important thing to notice about this equation is that it's proportional not to T, but to temperature to the fourth power, which makes the difference really significant. So if you have a 400 Kelvin object, right, 400 to the fourth power is a big number. 100 to the fourth power is also a big number, but it is much less than 400 to the fourth power. So the temperature difference effect gets modified dramatically by the presence of the fourth power in this equation. The second mechanism we're going to study is called convection. And the rate of transfer by convection is related to the area, a property of the individual sample, the temperature difference between different layers of the sample, and a constant that combines the properties of the sample and its surroundings, which we are abbreviating with a lowercase h in this situation. So let me go quickly through how convection works sort of qualitatively, and then we'll take one more look at the quantitative version of this, and then we'll come back. So the concept here is you have a container. For example, a container of air. And in one corner, you have a little flame, and you're adding heat to your container. When you add heat to the air expands and becomes less dense. As you know from previous work on buoyancy, if there is a less dense block of air down here in the lower corner, it's going to rise because it's less dense than its surroundings. When that block rises, a similar size block will slide in behind it. And then a similar size block will be dragged down from the far surface by gravity, right? It'll be allowed to fall. And the part that's being displaced will move over. So you get the formation of what's called a convection cell, which involves the bulk movement of material throughout. Notice that this is only driven by the temperature difference directly between the little chunk and its surroundings. And therefore, you're going to end up with a much lower rate of heat transfer at a given temperature difference due to convection than you would to radiation. The last mechanism that we're going to look at is conduction, and we have to set up a very special set of circumstances to talk about this. We have a high temperature hot reservoir over here. This is a high temperature hot reservoir on the left. On the right-hand side, we have a low temperature cold reservoir. So there is a tendency for energy to flow from areas of high density to areas of low density. So we're going to have a natural, spontaneous net movement of energy from where it is concentrated more on the left-hand side in this picture to where it's moving on the right-hand side in this picture. Now, there's going to be a couple of factors that are going to impact the rate that that happens. One of which is the cross-sectional area, which is labeled here in the center of this diagram. It's a little slice of this connecting tube between the hot reservoir and the cold reservoir. it is also going to depend on the length, right, the distance between the two reservoirs, the length that it has to traverse in order to move from the hot reservoir to the cold reservoir. And you would expect that an increased area would allow more heat to flow. There would be more parallel paths for the heat flow, whereas increasing the length that it has to go through increases the distance that it has to travel and would tend to decrease the rate of heat flow, and sure enough, it shows up in the denominator of the equation. So the area is multiplicative and the length is reciprocal, it's in the denominator. Our temperature change here is still T to the first power. So the rate of conduction through the solid is equal to this K value, which is a property of the material called thermal conductivity. This is a table of thermal conductivities given in watts per meter degree Celsius. Notice, for example, silver is an excellent conductor. Copper is pretty good, almost as good as silver, but not quite. Aluminum is a much lower conductor, and yet most of the heat sinks in our computers are made of aluminum and not silver. That, of course, is a cost thing. Aluminum is much cheaper than silver. So in order to get around that, we just increase the area of our heat sinks, and it carries heat away from our processors much faster, even though it's made of aluminum and not silver, which would be much better at transferring heat. And then we go on down the line. Air, as you can see, as most gases are, is actually a very poor conductor, which is why convection tends to dominate heat movement in air. There is some conduction, but it is quite small. And on up the list. Generally, we look at things that have conductivities less than 1 as being insulators. Good insulators, bad insulators, mediocre insulators. Concrete and glass are very similar. We use them for buildings and windows. Animal tissue, such as your muscles and fat and skin and so on, tend to average pretty low. We're pretty good at maintaining our heat, although we have a very large surface area. But we are not good conductors, even our music majors. Right? And then we notice that things like that we normally think of as conductors, asbestos, wood, cork, and so on, have even lower conductivities as we move on down the line. And again, air quite low, which is why double pane windows are such energy savers. So we've taken a look this week at phase changes, heating, and mechanisms of heat transfer. The next thing we will actually look at is a theory of thermodynamics itself, and that'll be coming up in the next group of lectures. This is a fairly small group of lectures material-wise, but there is a tremendous body of important problems that are addressed with this very limited number of concepts, which makes it good physics.